Okay. All right, folks, good morning. Let's start after a break of almost 1 week. So, so today we'll start design of microarchitecture, right? So we all understand what is microarchitecture is because we have spent quite some time about it. So we'll start looking at various components of microarchitecture first, and then we'll start combining them to create design of that. First, we'll look at the data part design, and then we'll go into control part design. And also we'll follow a sequence. First, we'll take up single cycle design. Okay, and then we'll once we complete single cycle design, then we'll understand how processor works, and then we will go into multi-cycle design. Okay, all right. Okay, just a minute. All right. Okay, so we will cover the following things today. We'll look at what actually microarchitecture is at the very top level, and look at some of these things which you have already studied in your course of digital logic design. So we'll go very fast today. We are doing it just for sake of completeness, and secondly, certain points that we are going to use in the design that I would like to emphasize. So it's today's course you can treat is something that you have already studied just for revision. Okay, so this is where we are. We are here. So you now, till now, you understand how high-level language work. Like you would have done Python and programming in C. But at this point in time, just think about language C because it's a compiled language. Basically, you have to compile it, not interpret. And then after compilation, you get assembly language program. Like this small program segment in C, you get this kind of instructions. Of course, these instructions that we are shown here is not in RISC. It's on some other it's actually in MIPS, but that's fine. So you get this kind of assembly language instructions, and then through assembler you convert this into machine level instructions. So we have studied what assembly language instructions are for RISC-V, and also we have seen what machine level instructions are. That's various formats we have studied. Now this program in this form is available to it, and also data is in this form is available. Now it is left how the underneath hardware, there's a microarchitecture is how microarchitecture will interpret this sequence of zeros. And this is where interesting thing comes, and this part of the course is really interesting. Okay, uh, and you can appreciate it. So now we are going to do machine interpretation of this zeros and ones, and this is done over some architectural components like ALU, register file, control unit, etc. And then if you go further down, then everything will boils down to sequential circuits and combinational circuits, right? Basically, we have gates and registers kind of uh, things, right? And of course, memory. Okay. So ultimately, we go down to this level. Uh, Actually, in this course, we'll not even go. We will touch upon this how different components can be created, like how full adder or half adder or all those things. Again, you have studied. Um for again, we'll just go through them very in maybe 10 minutes or something. I'll leave it to you to read it from the book. Okay, now it's very important for all of us to understand how computer works, because you are basically not only a just programmer, but also you are engineer who is studying either electrical engineering or computer science. Okay, so basically, so your understanding of system has to be better than the other programmers. And once you understand the system, how computer works, because it's a basic tool for you, then you can do better job. It's very similar to what a Formula F1 driver does. He need to know everything about the car, but or does he need to know about the car? Because car is a personality by itself, right? And the best drivers know their car very well. Okay, Shoemaker or whoever great F1 drivers have been, they know what goes on inside. Similarly, you need to know what goes inside. Okay, you just need not know only abstract level, like a ordinary taxi driver may not bother about internals of the car. Okay, but actual good ones need to know everything. So you need to know, because you can design better code, and that we have discussed earlier. And then you have to care about certain things like reliability, performance, and security, and all these things you can create. These characteristics you can bring into a system or your program if you know the architecture very well. Okay, and when we talk of microarchitecture design, we even at the microarchitecture level we bother about abstraction. Okay, so for example, you even when you're we you, as a designer, you may not really want to go to the level of how an adder is implemented, right? Because those designs are all available. Okay, so there is a abstraction that is uh, okay, there is abstraction that we use here even in hardware. For example, in the bottom level we have transistors, and from transistor we create combination logics, and then from combination logic we create sequential logic, and from sequential logic we create processors. Okay, because processor requires both sequential logic as well as combination logic, and then from processor, for processor we define machine level language. And machine language, actually a higher version of that, or sorry, higher abstracted view of that is in assembly. An abstracted view of assembly is high level language, and so on. And from high level language, and in fact, your grandfather need not know whether WhatsApp code that he must be executing, uh, actually is written in what language, C or whatever. So just then higher level abstraction is applications. Okay, so it means that the whole computer, because it's extremely complex, there is abstractions are used everywhere, both at user level. Users need not know anything. Okay, but even at architect level there are abstractions available, and you may have to go only to certain levels. Okay, all right, any question? No? All right, so what we have covered so far, we have covered this much. Okay, in this course we have covered, assuming that you have full understanding of C, we have covered this much. This is already covered in your previous course. Okay, and this is what we are going to discuss in next 12 lectures. Okay, rather more about, if you include memory, then another say 20 lectures. All right, so what is microarchitecture? So when we have looked at microarchitecture view in earlier classes, we say that this is not that is visible to a programmer. So this is, it means that this is a specific arrangement of registers, ALU, finite state machine, memories, and other combination logic blocks. Okay, and this can be, there are a number of ways you can design that, right? See, what we are discussing here, these are the components that each processor will have. Okay, but there is a way you can combine them, right? And each may give you different, and and different values also, right? How many registers, how many within ALU, whether is a single cycle design or multi cycle design or pipeline design, then depth of pipeline, how many stages are there in pipeline, then how many states are there in finite state machine, what is size of memory, what kind of memory, what is memory hierarchy, all that comes in the way you arrange these things. See, for example, in the house, if you are asked to build a house for yourself on a piece of land, then this, that I need two rooms for for certain thing. One, maybe one living room, one maybe a bedroom, one kitchen, one toilets, and so on, right? So there, or garage or whatever, right? So these are the basic things. But how do you design that? The size of room, or what other features it has, all that comes in the architecture or microarchitecture, if you have analogy, right? So this may not be so on. See, higher level, at top level, users may know, or as a programmer, you may know how many registers, but it may not know how many registers, what is register file in general, how many ports and all that, right? Okay, and as we discussed earlier, the architecture can vary depending on the requirements or application, right? So based on the requirement, we can design architecture or hardware, and these requirements could be basically at top level. There are only few: performance, cost, complexity, or maybe you can say reliability. Okay, so these are the few parameters that you have to consider while designing an architecture. Okay, all right. So let's start with the basic things which I think you would have studied earlier. Is First thing that you need to remember is that processors are synchronous devices or synchronous digital systems. Okay. Now, synchrony, concept of synchrony is very unique, right? I mean, very good. And in fact, in our life, we use synchronous system all the time. In fact, our body works, different parts of the body are autonomous, but there is a basic clock that drives everything, which is heart clock. Okay, and different body parts get synchronized using the heart clock. Okay, so in digital systems, we say that all operations of a processor or microprocessors are coordinated by a central clock. Okay, and imagine, different components. There are millions of components, and there is no synchronization among different activities, and input can come at any point in time, and output will be available at any point in time, and then there's all chaos. Okay, so it is necessary that all activities of processors are controlled by something which gives timing information, which says when state of system can change and when output will be available. All that is done using a clock. It's a heartbeat of the system. Okay, you would have studied this, right? So when in digital system in particular and processor in particular, when we say synchronous system, it means that there must be a clock. Okay, in the context of, see, synchronous and synchronous is quite confusing, in the sense that sequential circuits can also be asynchronous. Okay, when you don't use clock, it means the input is available at any point in time and output will be available after some time. Okay, while in case of communication, Ethernet, for example, we say is asynchronous. Communication is asynchronous, means that any process, any attached node can send packet at any point in time. But how packet, if it's in totality is asynchronous system, but each component within that, a receiver of a packet has to have a clock or derive clock from packet to receive that, right? So when you want to read a digital signal, zeros and one, right, there is a need for clock. even in asynchronous circuits, asynchronous communication mechanism. So forget about communication part. Just for rest of the course, excepting once when we study IO, uh, please remember that synchronous circuits will always use a clock that will define. This clock will say when transition can happen, or when signals can change, or when reading can happen, when writing can happen. Okay, all right. You would have studied combination logic circuits and sequential logic circuits, right? uh, I don't need to go through that. So sequential logic circuits actually form state elements which store the state of the system, and this is very necessary component. State elements are important for processor. Without that, we can't create a processor. Okay, so these state elements are registers and memories. Okay, all right. Any question up to this point? Yes, no?
No, sir.
All right. You would have done this course, right? This so now very quickly, another 5 minutes maybe we'll complete sequential circuit. Okay, this is a combinational circuit. Whatever input you give, instant, and after some time, very short time, output is available. It's nothing. It's just combination of inputs at that instant of time. Okay, so output depends only on current input. Okay, so but in processor we can't create um, a processor using only combinational circuit, because I mean, when you execute an instruction, you get data, but you have previous state that's useful, right? And because previous instruction has done something, you can't just forego it, right? Otherwise you have just one instruction execution, and that cannot be programmed, right? So previous instructions are state corresponding to that, or information corresponding to that you are going to use in next instruction, has to be there. Okay, it means that we are using a state machine where previous values are used in some way or other. Okay, it means that system has got to have some memory where these previous states information must be kept. Okay, and in order to that, we have storage element. Okay, so combinational circuit plus storage element forms a sequential circuit that you would have already studied, right? So in general, in the sequential logic circuits or in processors, we use state of the system, okay, for moving from one state to another state. So then what is a state in general, right? What can store state? So basically we can say that sequential logic might explicitly remember certain previous inputs, or might distill the previous input to a small amount of information called state of the system. Okay, so previous inputs, whatever it was, it has received and done an operation on that, and based on that there is some information available. Okay, that you are going to use further, or part of that information you are going to use further, and that's called state of the system. Because okay, uh, all right, and then we have the state of system. We define using state variables. So state variables we use, that contains information about past necessary to explain future behavior, or necessary for to get into next state or future behavior. Okay, all right. So where we can store this past information, we can store it in register, program counter, of course, and memory. Okay, all right. So now we will look basically a design of registers. Memory will touch later. Okay, and program counter is nothing but a register which counts the instructions. Okay, all right. So you would have studied flip flops. and you would have gone through this design bistable circuit to RS slash to D lash to D flip flop. We'll go over it in just 2 minutes, not more than that, and leave it to you to go through in detail if you have forgotten. Okay. Now we need a processor. Remember, cannot work only with combinational logic circuit because we need to control the flow of information. Okay. So if it's just combinational logic circuits, then there is absolutely no control. Okay, and the timing information, it's very difficult to get the desirable output when there are millions of components. Okay, so there is a need to control the flow of information. For example, when you execute one instruction, let's assume that you are using only combinational logic circuit. Okay, output is available, and then immediately you need to use that in output will go to a number of again hardware. Okay, different parts of process, and then it may create a lot of problem before even next instruction comes into play. Okay, so there is a need to control the flow of information. Okay, and that can be done only through registers or memory. Okay, this we have already discussed. So state elements hold up the movement of information at input to combination logic blocks to allow orderly passage. Okay, all right. uh, so this RS slash you would have seen. Okay, this is the first level where you have this kind of truth table here, that when R both R and S are 1, then Q previous, and 1 0 this output is 1, and 0 1 output is 0. This is very simple, and there is a one state which is invalid, right? So in order to overcome that, what we do is that this of course gives a reason why it is invalid. We come to gated latches, right? So we have this kind of structure where you use write enable. It means now with help of that, and there is only one input here, which is D, because we want to use this as a memory element, uh, or register element, or something, a flip flop which can store information. So we have just one input, and then we have seen that that previous column is gone. Now we have all state table which is quite clean, which is if write enable is 0, then we have previous, whatever previous in state was there, it remains. So q becomes whatever it was earlier, and it's a 1, then it changes, right? So if what write enable is 1, so whatever is at input we write it into system. So when write enable is 1, it's 0, then output is 0. Write enable is 1, input is 1, then output is 1. So it's quite simple. Now note that this is still not clocked, it's unclocked. Okay, we use write enable signal, and we have seen that this can result into certain problems that we'll discuss very shortly. Okay, before that concept of clock, note that processors without clock is not possible to design. Okay, uh, and this thing we have already seen that in combination logic circuits, different parts of you know see, the delay from input to output can vary depending on what is there in the path of combination logic circuit. Okay, there can be multiple gates in combination logic circuit, and totally depends on the execution one is doing. And then when there are different execution time, or what do you call that time the combination logic will take, at the end there is a need to synchronize it or store it somewhere before next you know computation can take place. Okay, uh, and that is possible only when there is something to synchronize, okay, which is nothing but clock. Okay, so it's basically all circuits on chip share a clock signal, and that tells every circuit when to accept inputs and how much time they have to execute the logic, when they must produce output. So basically what we do is that in single cycle design when, that we'll study, you have just one clock cycle available to execute an instruction, and then we have to define when we can write into a state element and when we can read from state element or register, for example. Okay, so this logic we define, and then we place different blocks in such a way that writing happens only once but reading happens throughout the cycle. Okay, so we'll look at that little later. Okay, so this is clock terminology you would have already gone through in your this logic course. This is a cycle time. Okay, so two edges are there in a cycle. Okay, so this is rising edge and this is falling edge. Okay, and we in our design, processor design, we will use only rising edge. So it means that all transition in a state element will happen only at the rising edge. Okay, so it's a edge triggered device that we will use. Okay, remember that. uh, so clock in general you would have seen when you have drum beats, it's like a clock signal. A heartbeat is also like a clock signal. And you would have seen parades, right, where there is a somebody in school, you would have possibly participated in that. Somebody, there is a use of drum for others to synchronize movements. Okay, uh, in 26 January you would have seen, this kind of parades, and somebody, there is a use of drum when all every soldier or every participant synchronizes the movement, based on the drum beat. Okay, and we know the frequency of that, right? I mean, our heartbeat is usually 1 second per heartbeat. Okay, but CPU, what is the clock speed? Okay, that we can use different speeds, right? I mean, different processor have different kind of clocks, and we can actually run the clock at different speeds also. So if 2.5 gigahertz clock is there, then cycle time or period is 400 picosecond. So this you would have seen. So I will not go in detail. So this is a clock. Okay. So basically in process you need to remember that, okay, we need to remember that at the start of the clock cycle, system state changes. Okay. So here at the rising edge, okay, system state changes, it stays same state for this duration. Okay, and of course we use edge triggered clocking where all state changes occur during a clock edge. Okay, all right, so and we use active edge or rising edge for clock transition or for a transition of state. All right, so this is again description of that. So what we do is that we have combination logic circuits. In between we have state, these registers, and that, so basically in one cycle, combination logic circuit should do its task, and then at the end of that, it gets, that state gets registered into a register, or yeah, in a register. All right, so so clock mechanism triggers transition from one state to another in a sequential circuit. All right, and combination logic circuit evaluates for the length of the clock cycle. Okay, we'll again see this, uh, and then this, what clock speed we are using totally depends on how much time this combination logic circuit is taking, because state transition happens in the you know so clock, so basically clock should be long enough for combination logic circuit to complete this task. Okay, so clock cycle should be chosen to accommodate maximum combination circuit delay, and clock edge acts as a sampling signal, causing value of the data input, causing the value of the data input to state element to be sampled and stored in the state element. Okay, so at the rising edge, whatever is the value that gets into state element and remains, and output remains at that till the end of the clock cycle. So remember this thing, okay? So sampling process is instantaneous. I'm sure you would have done this, in your digital circuit course. So we are just revising this because we, in our design, we are going to use this concept that in one cycle of the processor, instruction must be executed, and then all things, for example, is add instruction, the all addition, etc., should be completed within a clock cycle, and then at the end we are going to write the result into a register. Okay, so all these things should be completed within a cycle. Okay, all right. So now this is where we come. So in general, our processor design follows this kind of structure. Okay, so we have two state elements, state element 1 and 2. Output of this we use, okay, in combination logic circuit. Okay, and this should take whatever time it takes, c for example, should be enough that the computation is completed within the clock cycle. Okay, and then output is available here in the next state, and then at, if this is cycle time, at this point in time we are going to write into next state, next state element. Okay, so at the beginning we are going to use, because reading can be done at any point in time, so we can read this during the clock cycle or beginning of clock cycle. Let's assume we start from here uh, at this point, so we read it from here. Combinational logic will take some time to compute, and within the clock cycle output should be available before the next rising edge for data to be stored into state element. Okay, so clock edges sample those values for the storage in the state element. Any question to this concept? Please remember that this is very important concept, and we are going to use this throughout the design. Is it clear? हेलो,
Yes, sir.
नहीं आ रहा समझ में, पूछ लेना. Okay, all right. Now we are not going to go in detail into FSM. I'm sure you would have done that. Okay, it's just please go through this topic by yourself. Okay, so basically any system that we are going to design has got to have limited number of states. We can never say that computer has an infinite number of states. Analog systems have infinite number of states. It can have infinite number of values, but any digital system has got to have finite number of states. Otherwise, it's not possible to compute. Okay. Now we define behavior of the system. Okay, by system being in one state, and based on the inputs it receives, going into next state and giving some output in the process. Okay, all right. So human beings in general have infinite number of states, not finite number of states. That's the reason we cannot say person X and Y both born from the same mother at the almost at the same time, means the twins have same behavior. You cannot. Okay, while two systems designed by Apple have same model and everything same, will be, and given the same inputs, will be in the same state. Okay, so state, these are finite number of states, and then state transitions define the execution of a program. Okay, a system can be in certain number of states based on the input it receives. Okay, all right. So you would have seen this, so I'm not going to get into again details. So this already we have discussed. Okay, now in our context we have here a combinational logic circuit which we call it next state logic. because output of that we are going to use in system. Okay, and that will define next state. Okay, so if something is state information corresponding to is one previous instructions results. Okay, all right, and that will get stored into a state register. So basically whatever state information we want to take, whatever information we want to take gets into register or set of registers we can say, and then this output we use, and this note that this output is because of something that happened here. Okay, whatever is here, and that of course depends on inputs and previous states, is used in this combination logic circuit, and that gives some output, and we can use this also for feedback. So there's a knowledge, basically previous state knowledge comes from here. Okay, so we have next state logic, state register, and output logic. Clear? All right. At the beginning of clock cycle, next state is latched into state register. Okay, all right. So here, beginning of the cycle, we have state here. This is available. Okay, it totally depends on you again your design when you take do the state transition or when information get inside a register. But remember one thing is that at any point in time in any circuit, we are getting inputs from a combination from a combination logic circuit and getting in storing it into a register and using the output to next combination logic circuit. So essentially these are the two combination logic circuit blocks, and then output of that we are storing intermittently somewhere, and then it's going to next output logic, next combination logic circuit. All right. Okay, so this we have already seen, so we're not going to go into details. So now comes to the design of state register implementation. Note that this point is important. Rising edge trigger, it means that we need to store data at the beginning of every clock cycle. Okay, and data must be available during the entire clock cycle. All right. So if this is the input, okay, this is the clock, and this is register input. Okay, all right. Inputs, register input is that if this is register, this is the input. Okay, so the input is changing it to 1, and in between there is a glitch. It's becoming kind of becoming 0, and then remains here. So this is the input. Now what is going to be the output here? Note the transition, the value may be here as 1, but clock is low, and transition can happen only when rising edge. Okay, so now register output will change based on this, and it will remain, this is 1, so it will remain 1 until this becomes 0. Now if this becomes 0, note that there is no rising edge here, so it will wait for rising edge, and rising edge is happening here, then state transition will happen, the output of register will change to 0. Okay, any question? Any question? Aryan Yadav? Aryan, are you there? Aryan, माइक्रोफोन नहीं चल रहा है क्या? Okay, Deep Kumar,
Yes, sir.
uh, are you able to understand?
Yes, sir. Even this concept we read in our previous semester also applies in and everything.
Okay, all right, good. All right, so let's quickly go through it, right? All right, so you would have seen that how this problem of glitch is solved using, okay, so in normal latch we have this problem, the output also changes, okay, and if we design storage element like D type flip flop, okay, using master and slave, then we take care of this problem. Okay, so we don't have glitch, and whatever input goes into a rising edge is available throughout the cycle. So this is the reason we use D type flip flop to design a register. All right, so now we will not get into this kind of structure when we discuss registers, rather we'll use this kind of representation, and we say, and this is a D type flip flop, and then we say the state change happen on clock edge, which is rising edge, and data is available throughout the cycle. This we will have to remember. Okay, and now we can use this kind of flip flop to create registers, right? So now we have rising edge triggered flip flop, clock flip flop that we can. So this kind of flip flop, which is represented this way, we can use to create registers. Okay, all right. So this is very simple, and note that timing, right? So this is a clock edge, okay, and this is the input, which is 1. The output, which is q, is available only after some time delay. Okay, because this thing is going to take some time. Okay, from input rising as this input to output, which is q, it will take some time for the whole thing to happen. Okay, and this time becomes very important. We'll get into more details later. Okay, when we study design of okay, kind of registers. Okay, so this is a register where we put in many D type flip flops in parallel. So we can say when we put 4 flip flops, then we say that here there are 4 bits we can store. Okay, so say in RISC we use 32-bit registers, right? So basically it will have 32 such D type flip flops. All right, okay. So this is one design of a register. Okay, this is 4-bit register. All right, okay. So this is largely about what we want to discuss today. So we in general we need to remember that processor design requires use of finite state machine. Finite state machines we can create using combination sequential logic circuit. Is important to have use registers or storage element to create a finite state machine. Okay, uh, and then we have seen that we are going to use clock signals, and state transition or writing into a register will happen only at the rising edge. Then clock has within a cycle there is a rising edge. Okay, and there's one rising edge. Okay, in that rising edge we will do the writing into state element or register, and throughout that cycle, throughout that period, clock period, that output is available at output port. Okay, of course there is some delay that we will see in, we will see how we can there is delay for certain period of time. This input signal should remain stable, and then of course this input also should remain stable after this rising edge for certain period of time, and there is some delay which we call is you know uh, when the output is available at output port is called click to queue delay. You will see later, and based on all these delays, from when signal is coming to input to is available to output plus combination logic delay. Okay, before the output of combination logic goes to some register again, that should be that all these things should happen within a clock cycle. So clock should be big enough for accommodate all these things, that is state transition in register and time required for combination logic circuit. So all that we've summed these two together, it should be less than the clock period. All right. Okay. All right. Any question? Okay. Let me just stop recording.